It's great to be here. Um, so as was said, Kate Chilton, I am the Chief of Staff as well as the Chief Sustainability Officer at Bamcore. I am going to talk today about fast-growing fibers and particularly timber bamboo, which is one of the fast-growing fibers that we use. Um, I was going to start off by talking about why fast growth matters, but I'll quickly go over the slide because Jacob covered a lot of it in his presentation, but really two main reasons. The first of which is time value of carbon, this idea that emissions reduced today are worth more than those that are emitted or reduced in the future. And this is due to tipping points, as well as the idea that early action will actually give us time in order to implement mitigation measures, as well as give us time to adapt to the changing climate. So then the other reason is that fast-growing fibers have the potential to achieve net cooling. Again, Jacob mentioned this. If they store more carbon than they emit, that means that they're carbon negative. And the time at which they can achieve that net cooling is really correlated with the rotation cycle and how fast they can grow. So you can see here in this graph that the concrete and the steel only ever increase emissions because they don't have that follow-on regrowth to sequester carbon. Wood and all these other bamboo or bio-based materials, they have downward slopes that eventually achieve net cooling because in these examples, they store more carbon than they emit. However, it takes wood decades, sometimes close to 100 years to reach its full harvest cycle versus bamboo and these other annual crops, because they grow faster, they can be harvested much sooner and then potentially reach that net cooling a lot faster. And then as Jacob noted, it's really important to remember that traditional LCAs that underpin EPDs, which communicate the environmental benefits of these products, do not account for timing of emissions. They do not give fast-growing fibers credit for their speed of regrowth. And so trying to incorporate dynamic LCA approaches into these standards, I think, is going to be a big push for the upcoming years. So onto timber bamboo. It's an amazing fiber. It's where Bamcore's origins lie, and there's a number of reasons why it's really special. And so the first reason it's being that it's really fast growing. And with some species it can grow a foot or more every single day, and it reaches maturity and has really short rotation cycles. So individual clumps will reach maturity in 5 to 7 years, depending on the species. And then every single year after that, they can be partially harvested. Individual culms within the clump can be partially harvested. So you can have perpetual annual harvesting every year after. And this is really key to the carbon sequestration story. So when you think about bamboo's carbon sequestration potential compared to wood, if you take a tree and you take a culm and just compare them statically, the wood and typically the tree will store more carbon. It's generally bigger in that sense and it can store more. But over time, if you have this perpetual harvesting mechanism, you're able to sequester a lot more with timber bamboo. It's also extremely land use efficient, requiring a fraction of the space, which is incredibly important when we think about the global land squeeze that we're experiencing. There's no clear cutting when you harvest, which is different than wood. So this is important for minimizing soil disruption, so you don't have that constant replanting. And it promotes biodiversity by keeping the whole system intact instead of having this really harmful clear cutting practice. And then finally, it's really restorative, or it can be. It's able to grow on degraded lands and it can reduce soil erosion. So in a lot of places, you're seeing projects where they're using timber bamboo for restoration in order to satisfy dual goals of carbon sequestration and soil restoration. When we think about building with bamboo, there's really two categories, largely speaking. The first of which is what's called whole pole construction. This is much more common in Southeast Asia and Latin America. And it's when you take the entire bamboo pole, you process it very minimally, and you use that to create the structure of the building. Versus engineered bamboo products, these are emerging. They're much more common in North America and Europe. And they're much more similar to the wood industry and how plywood and LVLs and glulam are made, in that they're processed. You use glues and resins to adhere them into panel-like structures. And so the next slide and the slide after, I'll be focusing on this engineered bamboo products category of construction. And so despite the impressive mechanical properties of timber bamboo and the other sustainability benefits that I just mentioned, engineered timber bamboo has yet to achieve really meaningful widespread adoption. And the main reason is because it's not currently cost competitive with traditional building materials. And so builders don't typically want to pay that green premium that's associated with it. And so in this paper that I have shown up here on the slide that I wrote with my colleagues, we outline the main problems that we see as preventing timber bamboo from being cost competitive, and then we propose solutions to those challenges. And so I'll summarize the four kind of categories of problems and possibilities here. The first of which is limited commercial plantations. So there's a small total hectarage of commercially managed bamboo worldwide. And the ones that do exist are typically smallholder bamboo farms. And they can face difficulty in selling their product because of some of the problems of having small scale economics. So this is things like limited bargaining power and market connectivity. In addition, without consolidated commercial scale feedstocks, dispersed harvested material has to be transported and consolidated into central processing centers, which then further increase the costs from transportation and handling. And so to remedy this, it's all about incentivizing the establishment of bamboo plantations. And there's two examples that we include in the paper. The first of which is national commitments to use bamboo for land restoration. This has been reported twice in the recent past by member states of INBAR, and then also carbon credits to support the establishment of timber bamboo plantations. And a great example of this is EcoPlanet Bamboo, who is doing this in Nicaragua, in the Philippines, and elsewhere. The next category is harvesting technology. So lack of investment in harvesting technology is really the problem here, and this harvesting technology is critical to having cost-effective raw material supply. So today, bamboo harvesting remains almost exclusively manual in comparison to the wood industry that has had over 200 years of continuous R&D of harvesting technologies. And that's resulted in mechanization and in some cases, full automation. And so for the wood industry, that's resulted in decreased harvest costs and time to harvest, as well as increased yield recovery. In addition, unlike commercial wood harvesting, bamboo is not clear cut. As I said, this is a benefit ecologically speaking, but the selective partial harvesting approach that is associated with timber bamboo harvesting actually complicates the process significantly. And so to mitigate this, we propose two paths forward, the first of which is retooling wood harvesting equipment. So successful retooling of the equipment will need to accommodate for the unique factors or the unique features, I should say, of timber bamboo. So this is things like the culm diameter being smaller, the culm being lighter than solid wood bowls. The optimal crosscut is usually fairly close to the ground, and the bamboo is harder to cut itself. So that'll generally produce faster dulling of the saw teeth. So all things that bamboo harvesting equipment needs to account for. The second is scanning technologies that can potentially generate increases in yield recovery. And so at the culm level, terrestrial laser scanning technology can determine a culm age, which can help identify the optimal culms to harvest within the clump. And then at the clump level, geospatial LiDAR application can determine accessibility to individual culms within the clump. And so combined, these two can create ideally an optimal harvest order map that informs harvesting decisions. Third, we have processing and manufacturing. So this stems from low yield recovery due to timber bamboo's unique properties, again, relative to the physical shape and morphology of timber bamboo. It has several properties that make processing inefficient and efficient processing really challenging. And so it has a tubular hollow structure. It has a hard waxy outer layer. It tapers significantly at the top. The nodes have bulges that you account for, and the thickness of the culm wall itself varies. And so in addition to all of these properties, the conventional slat processing that's used today that makes the majority of engineered bamboo products involves milling a lot of individual pieces, the slats, and then adhering them together into panels or other pieces. And that process is very manual, it's very time consuming, and it results in severe yield loss. So both of these things can contribute then to the increase in cost. And so a potential alternative to slat processing is densification, which involves flattening the bamboo as a way to increase yield recovery. And then another possible approach that we propose in the paper is what we call property-based multi-product recovery. And so from the bottom to the top of the culm, the characteristics like fiber density, culm wall thickness, like I said, even circumference, they change based on the section. And so this is the idea that if you decompose the bamboo culm into these distinct sections and then process them according to their unique properties, you can have a range of products that ultimately help minimize waste because you're utilizing more of the culm. And so an example of this could be the top of the bamboo being used to make scrimber, the middle portion of the bamboo to make laminated bamboo lumber and veneers, and then the bottom being used to make densified strips, as an example. And then the final bucket is market application. So this is the idea that the superior mechanical properties of bamboo are not being fully utilized in the low-rise market. And even if the improvements that I just made across all these other areas still don't let bamboo compete with low-cost alternatives like wood, then bamboo needs to be repositioned. And so in addition to increasing yield recovery, densification can reconstitute the fibers to have significantly more load capacity. And so what this means is that it could potentially produce a new generation of bamboo building products that compete outside of the low-rise market and serve as an alternative to steel in multi-rise and commercial construction. And there's really two benefits to doing that. One, there's much greater carbon reduction opportunity of displacing steel instead of displacing wood. And also the higher end use of the bamboo means you can charge a higher price, which means you can offset the higher cost. And so all key things to think about when trying to overcome this commercialization challenge that bamboo faces. And I'll end by kind of sharing how bamboo is walking the walk, not just talking the talk. And so we have a research grant from the Department of Energy that is focused on this fiber densification research. And so you can see here, I have visuals of the different slat processing and flattening and densification methods. So you can see how they differ. And again, here really the goal is to lower the cost of bamboo processing such that it can better compete with wood-based products, and then also increase the value such that we could potentially have it compete in a whole new market with different products like steel. And with that, I'll leave it to questions.